Let's start by talking about the worst possible running time. Well, what gives us the worst possible running time? It's when we have to search the largest possible amount of array. So let's just say we're looking for, I don't know, the n over 2, the median value. So that's the order statistic we're looking for, is the n over 2 value. What would be the worst possible pivot choice? Well, what maximizes the amount of space that we have to look at? Well, if I have all n elements, and I'm looking for the middle element, let's say I partition it into 0 elements and n minus 1 elements. Well, now I have to search the n minus 1 elements. So our worst pivot here is the same as the worst pivot that we had for quick sort, which is if we take the minimum or the maximum values. What's our best possible running time? So this is kind of an interesting question. What's our best possible running time, and sort of also think about what are the conditions that arise to that best possible running time. Well, when I ask you about the running time, you could think total running time or asymptotic running time. In this case, our best running time is going to be big O of n. And an easy way to think about that is, well, what happens if I get lucky and the pivot element is the element that I want to return? So if I jump back to our code, what happens if I hit this case? Well, you might be tempted to say, well, that's just a constant lookup, so our best possible running time is constant, but that happens after our call to partition, which is linear. So we could have to call partition once, and then we get lucky and we return our value. So best possible running time is going to be linear, big O of n. And in fact, it's going to be just whatever the running time of partition is plus a couple of extra constant operations. An interesting artifact of this is that you're more likely to finish the algorithm in linear time than in the worst case running time. So this worst case running time to complete it was quadratic. That's if I continually get really bad choices for the pivot elements. So you're actually much more likely to finish this in a single call to partition than you are to always get the worst running time. So what's the probability that you get this absolute best case possibility of only calling partition once? That's a 1 in n probability, which is small. But what's the worst case? Well, it's a 1 in n to get the worst possible pivot, times a 1 in n minus 1 to get this again get the worst case possible pivot, times another 1 or n minus 2 to get the third worst possible pivot. So your chances of getting that worst case where you're always getting the min or maximum element as a pivot really start to decrease the more elements you have in your array. You're not very likely to have this worst case actually happen. So under normal circumstances, what do you expect to be the best possible choice for the pivot? Well, let's say it's for any general ith order statistic. Your best possible pivot element is again going to be cutting the array in half. So it's going to be your median value. Alright, so we know that we're looking for the median value. And what would the running time be if we always deterministically pick the median? Well, this is kind of a trick question. How would I compute the median? How do I find the median deterministically, guaranteed to find the median? Well, the only guaranteed way to do that would be to have an algorithm that's guaranteed to give you the n over 2th order statistic, which is what we're trying to develop here. So it's kind of tricky, but suffice to say that it's not an easy amount of work, and in fact, it's pretty reasonable to expect this to take sort of n log n amount of time to deterministically find the median. So basically sort it and then pick out the median. It's not the fastest absolute way to do that, but it's reasonable to think about that as the way to deterministically pick the median. Okay, well, clearly we don't want to do that, because if we're going to sort it, let's just get our value, our order statistic from the sorted data instead of just then going on with quick select. So we're not going to end up doing that. We're not going to deterministically pick the median this set of slides. We'll talk about something similar in the next set of slides. It doesn't do this exactly, but it's close. All right, well, what if I told you that the algorithm always picked the running time? How would you calculate the running time? Another way to ask that is, what tools do we have at our disposal if I tell you that this is going to deterministically always pick the median? Well, it might again help if I'm a little more specific. Here I'm talking about getting the asymptotic running time. And if I tell you that, then maybe you would say, well, if I know I'm deterministically always splitting in half, I can use the master method. Because I'll have one recursive call. I will have half the data after each in each recursive call. And I know I'm calling partition, which is a linear amount of work, so d is equal to 1. So that's going to give me a recurrence equation like this. So that's my recurrence. T of n over 2 plus big O of n. What that will lead you to is a big O of n running time. And I'll leave that as an exercise up to you if you want to figure out which case that is and see where you end up.